Welcome to The Explainer. Today, we're digging into a hidden history of mathematics. We're going to look at the foundational operating system that powers so much of our modern world, and, well, we're going to discover that its origins are probably not what you were taught in school.
Okay, so let's just start with a big question, one that kind of challenges the whole story we're all taught. You know the one, we learn about the ancient Greeks, then there's a big gap, and then suddenly the Renaissance in Europe. But what if a crucial 1,000-year chapter was just left out? What if the key innovations we attribute to later periods actually happened much, much earlier?
And this slide, this is where it gets wild. Look at the gap. On the left, you've got the conventional timeline for these huge mathematical breakthroughs. But on the right, a much, much earlier origin story. We're not talking about a small correction here. We're talking about a difference of centuries, sometimes a whole millennium. This is a fundamental rewrite of where the tools of modern math were actually engineered. To find the source code of modern algebra, we're not going to 17th century Europe or even 9th century Persia. No, we have to go all the way back to 7th century India and meet a genius named Brahmagupta. And get this, he wasn't just solving for x, he was building the entire system that makes solving for x even possible.
It all centers on this one incredible text from the year 628 CE, the Brahma-Sphutta Siddhanta. You should think of it less like a textbook and more like an architectural blueprint. Brahmagupta wasn't just scribbling down equations. He was designing the entire system, the very language and logic of algebra itself.
So, the first pillar of his system was something he called Avyakta Ganita, which literally means the mathematics of the unknown. This was the formal, systematic use of symbols. He used letters, even colors, to stand in for unknown quantities. That simple idea, letting a letter like X stand in for a number you don't know yet, that's the absolute bedrock of all algebra. It starts right here. Next up, he took the concept of zero. Now, for a long time, zero was just a placeholder, right? Like an empty spot. Brahmagupta elevated it into a full-fledged number. He gave it rules. He defined how it behaves when you add it, subtract it, or multiply by it. This was a monumental leap in abstract thinking. And he didn't stop there. He laid out all the rules for positive and negative numbers. He used these really simple, intuitive ideas of fortunes and debts to explain abstract concepts, like why a negative times a negative has to be a positive. What he created was a complete, unified number system that just worked with perfect consistency. But okay, let's get to his most profound contribution, because this is where things get truly mind-blowing. We're talking about an idea so advanced, it feels like it was beamed back from the future. It's called the Bhavna, or the principle of composition.
And hey, don't just take my word for it. This isn't just some historical curiosity. This is a concept that stuns top mathematicians today. The quote here is from Manjul Bhargava, a Fields Medal winner. That's basically the Nobel Prize for mathematics. He points to this specific work from the 7th century as being completely revolutionary.
So what is this Bhavna? Well, it's this incredibly elegant, almost magical law. Brahmagupta figured out that if you have a really complex equation, like the one you see here, and you manage to find two different solutions for it, you can then compose them. You can combine them using his special formula to instantly generate a third, totally new solution. This ability to create new solutions from old ones is a cornerstone of modern number theory.
And just look at this timeline. It's amazing. This one idea from 628 CE creates a direct thread to the work of Carl Friedrich Gauss, one of the greatest mathematicians of all time, over 1,000 years later. And that thread continues right into the 21st century, forming the basis for the very work that won Manjul Bhargava that Fields Medal. It is an unbroken intellectual legacy stretching over 1,400 years. Now, the story doesn't end with Brahmagupta. Fast forward 5 centuries. Another master, Bhaskaracharya II, takes Brahmagupta's incredibly powerful algebraic tools and points them towards the heavens, using them to solve the deep problems of astronomy. He started tackling concepts that European mathematicians would struggle with for centuries. You know the big one, division by zero. While pretty much everyone else just called it undefined, Bhaskaracharya gave it a name, Kahara, and he gave it a rule, any number divided by zero equals infinity. This comfort he had with the infinitely large and the infinitely small, it led him somewhere incredible, to a place that our history textbooks usually say wasn't reached until Newton and Leibniz in the 1600s, the very edge of calculus. See, to do his astronomy, he had to answer a critical question. Planets don't move at a constant speed, right? Their speed is always changing. So how do you figure out its velocity?
Not over an hour or even a minute, but at one single, precise instant in time. That very question, that is the heart of differential calculus.
And his solution was, well, it was breathtakingly modern. He analyzed what happens in the smallest possible sliver of time, an infinitesimal moment. And by doing this, he was able to calculate how the sine of an angle changes at that exact instant. He had effectively discovered a fundamental concept in calculus, the derivative of the sine function.
The proof is right here. On the left, you've got Bhaskara-Acharya's formula from around 1150. On the right, the modern notation developed 500 years later. Yeah, the symbols are different, but the mathematical relationship, the core idea, is identical. He found the derivative.
So why does any of this matter? I mean, it's more than just historical trivia, right? It redraws the entire map of scientific history. It forces us to ask some pretty serious questions about where modern knowledge actually comes from. So let's just recap the breakthroughs we've talked about. A complete systematic algebra, a composition law that is still relevant in modern number theory, formal rules for infinity, and a key discovery in differential calculus, all of it originating in India, centuries, even a full millennium before the standard timeline we all learned.
And that leaves us with one last thought. This isn't just about the history of math. It's a powerful reminder that entire histories of innovation could be hidden in plain sight, just waiting for us to look a little closer and to reread the chapters we thought we already knew.